Hi, and welcome to our discussion. We've got a PowerPoint presentation here on wind speed measurements. Specifically, we're looking at speed sensors, and even more specifically, we're going to talk about wind profilers today. So first, we'll start out with the theory behind wind profilers, how they work. We'll talk about the different types and the pluses and minuses of using wind profilers to measure the wind. First off, what exactly is a wind profiler? Well, basically it's a vertically pointing radar. A vertically pointing radar sends electromagnetic radiation pulses through the atmosphere, in this case vertically. And they operate in the VHF or UHF range between 30 megahertz all the way up to 3 gigahertz. And looking at the graph there, it shows that 1 gigahertz is kind of in the microwave range. So these are basically very close to microwave or VHF at the upper end of the VHF, and then also microwave. These radars are sending out signals vertically through the atmosphere. What they're measuring is the Doppler shift. In other words, the Doppler shift, if you remember your radar theory, is when a signal goes out at a particular frequency and it comes back at a different frequency. And that change in frequency is a result of the motion of the object either towards or away from the radar. So Doppler radars measure radial velocities, either towards or away from the radar. And specifically what wind profilers are looking for, they're looking for turbulence in the upper atmosphere. They're trying to, the turbulence, these little eddies and swirls, or these changes in refractive index in the atmosphere result in clear air returns. Now we're assuming that these little swirls are moving along with the wind, so if we know if we get a return back from these little swirls, these little discontinuities in refractive index, then we can measure how fast they're moving along based upon Doppler theory. So it's kind of complicated. Gets into radar theory, and we're not going to get too deep into this, but basically what Doppler, or not Doppler, but wind profilers are looking at are clear air returns, or clear air echoes. And by definition, a clear air echo is a radar echo that comes back from someplace in the atmosphere where there doesn't really appear to be any targets, such as cloud droplets, snowflakes, or any other kind of meteorological scatterer that can return radar energy. So basically, you don't see anything out there, but you're getting radar energy returned. And that radar energy is coming back off of these little discontinuities in the atmosphere. So the clear air echoes are caused by either solid targets, things that you may not necessarily see, like particulate matter, dust in the atmosphere, birds or insects or things. But what wind profilers really are looking at, and what they're keying on, is spatial fluctuations of the refractivity that are on the size or on the order of radar wavelengths or smaller. Specific radar wavelength, smaller than that wavelength, then you'll get a return. In radar theory, they call this Bragg scattering, and you'll see that with turbulence. And then also, you might hear a term called Fresnel reflection, where you have really strong strong discontinuities in the atmosphere, whether it be temperature or density, that result in a return bouncing off of these discontinuities in the atmosphere. So these are, of course, high-powered radars sending up a signal at particular wavelengths, and you can actually detect the motion of the air from these swirls or these discontinuities that are moving along with the wind. They send back a signal. They bounce off of the radar signal, bounces off of these strong refractive index fluctuations. In other words, temperature or density in the atmosphere, and they come back to the radar. So wind profilers use Doppler velocity techniques to measure the wind. As we said, Doppler, the theory, can measure the radial component. So it can measure whether the wind is moving towards or away from the radar with respect to the beam. Since these are vertically pointing radars, it can detect whether it's moving away from the ground or towards the ground, which seems kind of strange. So that's not a perfectly vertically pointing radar or wind profiler really doesn't measure much, just whether the air is going up or down. What we want to know is whether the air is moving horizontally. To do that, they have to tilt the radar beam, I should say. And they use 3 different tilts. And because of that, because they swing the beam, then they can measure the radial velocity in 3 different components, and they can combine those to figure out the horizontal wind. So the way they do this is they use a phased array antenna. This is one where the antenna doesn't actually move. You think about radars, a common radar. It's got a big dish that spins. These don't have a big dish. As a matter of fact, these wind profilers look more like bed springs. And what they do is they can energize the antenna at different times. So they don't energize the entire antenna, but just parts of it. When they do that, that actually sends out a pulse of radiation that's determined by how you energize these individual antenna elements. And it actually goes out at an angle. And how you energize it determines how you energize each segment of the antenna determines the angle that it moves away from this particular antenna. So this is what it kind of looks like, an artist's version of what a phased array antenna looks like. Phased array antennas really have no moving parts. So servos don't break down. You don't have to raise the elevation angle or anything like that. They basically steer the radiation beam or the radar beam at a particular angle based upon how the elements are energized, the antenna elements. So this is how a wind profiler works. The radar beam, the beam, tilts in different directions. It can determine the horizontal and also, believe it or not, the vertical component of the wind. And this beam sequence, this rotation, or tilting, I guess you should say, happens between 1 to 5 minutes. It can do that. And then, as I mentioned before, as the winds are moving along, we're assuming that the little swirls are moving along with the wind. We can measure the Doppler velocity, and based on that, we can back out and figure out the radial velocity. And then tilting the beam different directions, we can get the 3-dimensional wind in the upper atmosphere. So wind profilers are pretty slick technology. They operate at higher frequencies. That means shorter wavelengths. And operating at higher frequencies, the higher the frequency or the shorter the wavelength means that you need a smaller antenna. Big antennas are for longer wavelengths, shorter wavelengths, smaller antennas. And of course, with shorter wavelengths, that means that the little discontinuities that you're looking at in the atmosphere are smaller than the size of the wavelength. So you're looking at really small turbulent flow fluctuations in the atmosphere. And then with shorter wavelengths, also you get a really good resolution in the atmosphere. You can look at several layers, and you're not looking at a kilometer deep, but you're looking at only maybe meters deep or tens of meters deep. And then of course, as wavelengths get shorter and shorter, radar theory tells us that shorter wavelengths we tend to have higher attenuation, which means that the radar energy is dissipated rapidly as it moves away from the radar, which means that short wavelengths or high frequency radars can't see very high into the atmosphere. So that's a quick overview of the theory behind wind profilers. And we'll get into the different types of wind profilers that are available and that are used today to measure the winds in another video.